Good evening to all. Welcome to the 26th lecture of the course Experimental Methods in Thermal Engineering. In our previous lecture, we have started discussion on the measurement of temperature, and in particular, I have divided the measurement of temperature using two methods. One is based on the mechanical methods, and second is based on the electrical approach. Okay, so we have covered different type of thermometers which are based on the mechanical measurement techniques, and then we have seen some of the advantages of the electrical methods over the mechanical methods, which are mainly uh, required in order to design the feedback systems or to obtain a controller for some designing some experiments. Okay, so we will continue our discussion once again today also on the measurement of temperature, and as we started our discussion on the electrical method, so few electrical methods still we have to discuss. So I'll now start our discussion with the measurement of temperature based on thermoelectric effects. Okay, so, what is this thermoelectric effect? It is actually what we are doing. We are trying to convert the change of temperature effect into nothing but some electrical output. Okay. So, the device which is used, that particular device is known as thermocouple, and thermocouple is a very popular device for measurement of the temperature. In majority of the times, while we measure temperature, actually we try measure the temperature using the thermocouples. Okay, so large number of thermocouples are commercially available. So using these thermocouples are mainly employed for measurement of the temperature in industrial as well as the lab-based experimental setups. Okay, so what we are having basically in this particular arrangement, we are having the wires of two different materials. So for example, one this thick wire over here is represented. It is of some material 1, and another wire we are having, this is of actually some other material 2. Okay. So we are having actually wires of two different materials, and these two wires are meeting at some point. Okay. So the point at which these are meeting, that is nothing but some junction. Okay. And now let us consider that this junction is having some temperature T. Okay. So now what we are having basically, we are having two other ends of the wire which are opposite to this junction. So if this junction is having some temperature and we are having the material of these two wires as different, what will be happening if we are measuring the voltage across these two terminal points A and B, we will be finding some output EMF. Okay, so some output voltage will be generated. So this particular type of effect is nothing but it is known as Seebeck effect. Okay. So for example, what will be happening if you are having some temperature T1 at the junction, you will be getting some corresponding value of output EMF over here as E1. Then if you are changing the temperature to some other value T2, corresponding to that you will be getting some another output E2. Okay. Now, obviously, while we will be employing this type of device for measurement, so we will be having some external circuit over here, and that circuit will be actually obtaining the value of this output voltage, and that will be then finally displaying it in some readout. Okay. So, while we are having the external circuit, obviously, because this effect is basically generating some voltage. So if there is some generation of certain voltage, obviously some current will be flowing through this circuit. Okay, so we will be having some current through this entire wires and this circuit. Okay, so what will be happening? The flow of current, particularly through this external circuit, will be actually altering our value of the EMF, whatever we are getting. Okay, so we will be having some alteration in the value of EMF, output EMF, whatever we will be getting. And why we are having alteration? Because some current will be flowing inside that. So particularly, whatever the alterations will be happening inside the value of EMF because of the flow of current in the external circuit, that particular effect is something which is known as Peltier effect. Okay. So that particular effect is known as Peltier effect. Another important thing, what will be happening, we will be having some temperature over here, and obviously through this other ends of the wire or throughout this length of the wire there will be some other temperature. Okay, so if we are having sufficient thermal conductivity of the wire material, in that case what will be happening, there will be transfer of heat or conduction of heat from this particular junction towards the length of the wire. Okay, so we will be having certain conduction of the heat along the length of the wire. So because of that, whatever the these measurement wires we are having, uh, along the length of these wires also we will be having existence of some thermal gradients. Okay, so ultimately what will be happening, these thermal gradients will also be actually changing the value of the output EMF or output voltage. Okay, so particularly the changes or alterations in our output voltage because of these thermal gradients inside the wire is particularly known as Thomson effect. Okay, so what is basically happening? The principal idea was of using two different material wires, and these we have created some junction. So because of that, we were getting some output EMF. Okay, so that principally that effect is nothing but a Seebeck effect. Okay, but while we have done so, we have used some external circuit, certain amount of current will be flowing, okay, into the circuit. So because of that, we will be having certain alterations in our output EMF. So the effect which includes the flow of current also into the circuit, that effect is something which is known as our Peltier effect. And then as we are maintaining this junction at certain temperature, so because of that, what will be happening? Obviously, this temperature is nothing but the temperature which we want to measure. Okay, so because of that, what will be happening, ultimately because of the thermal gradients which are existing inside the wire, because of that also we will be having some alterations in our output EMF which we will be obtaining from this type of arrangement. So that particular effect uh, in our EMF which is induced because of the thermal gradients, that particular effect is something which is known as Thomson effect. Okay, so principally our aim was to utilize the Seebeck effect, but while we are using this Seebeck effect, we are having few additional things because of the inherent nature of the phenomenon which is happening over here, and these two things particularly cannot be avoided. So because of that, we will be having certain alterations in EMF over here. So finally, we have to, in our actual measurements, these effects will also be coming into consideration. So the final idea is that one side we will be having actually temperature. Okay, then these three effects will be actually participating simultaneously, and these will be actually giving us some final value of the EMF. So we will be getting some output corresponding to some temperature of the junction. Okay, so that is the whole idea, that we are having this material of the wires in such a way so that if we are joining these two wires and we are maintaining certain junction of temperature, so corresponding to that we will be getting some output. Okay, so this is the whole idea of using this particular arrangement. Now we may have additional number of wires. For example, one another arrangement is shown over here. So we are having some material 1 and material 2 as usual, and now instead of making the junction over here, we have used some material 3 over here, which is actually now leading to two more connecting points C and D. And if we consider that the temperature of point C and point D is same, in that case, whatever the output voltage we were getting before, same type of output voltage we will be getting if we are having same value of temperature. Okay, so and in case our temperatures are changing in these particular two junction points, then obviously we will be having certain EMF production within this wire also. In this arrangement also we will be having particularly because of the Thomson effect, we will be having some alterations in our output EMF. Okay, now one thing is considered over here. For example, if we are having a situation that we are having two bimetallic wires. So one wire is actually shown over here, this thick normal line, and then another wire we are having over here, this thin wire. Now, if we are having two junctions, and let us consider that first junction is actually having temperature T1 and second junction is having temperature T2, and from this arrangement we are getting output voltage as nothing but E1. Then we are having another arrangement where the junctions are maintained at temperature T2 and T3 and we are getting output as nothing but E2. Okay. Now, if we just use exactly identical wired materials, okay, and exactly identical structure, and now if we just make these two junctions of our this particular mechanical arrangement at the extreme temperatures T1 and T3. Okay, so now we are actually avoiding this intermediate temperature and directly we are maintaining the temperature T1 and T3 at our extreme junction points. So corresponding to that, let us consider that if we are getting this output voltage as nothing but E3, so what will be happening? This output voltage of E3 will be nothing but equal to E1 plus E2. Okay, so this particular kind of intermediate temperature theorem, whatever you are getting over here, that is actually, if you take just the boundary temperature, then your entire EMF will be actually the sum of the EMFs which you have obtained while used the system with the intermediate temperature condition. Okay, so that is some common relationship or universal law that is which is applicable to our thermocouple arrangement. Okay, now what we have done over here in this previous slide, we have seen that if we are having certain junction in between the two wires, so obviously we will be getting certain output voltage. Okay, but what will be happening to the absolute value of the temperature? Because if we have to measure the absolute value of the temperature, then obviously we should have some reference point. Okay, so either we should have some known standard against which we can actually compare that, okay, with the reference we are getting this much voltage, and when we are changing the temperature to some other value, then what we are getting. Okay, so obviously if we have to obtain the absolute value of the temperature, particularly we require some reference temperature, okay, or some reference junction. With respect to that reference, actually we can obtain the value of temperature depending upon the amount of EMF we are obtaining. Depending upon that, actually we can relate our temperature at the junction where we want to do the measurement. Okay, so what we have done over here, we are having nothing but a constant wire. So this particular wire is nothing but a constant wire, and then we are having one iron wire. So these two are connected at some junction T. Then what we have done in this particular arrangement, now we have actually created two reference junctions. Okay, so this iron wire is connected to a copper wire at this particular reference junction, and then this constant wire is also connected to a copper wire. This is also actually considered as nothing but a reference junction. Okay, and what we are doing now, we are particularly measuring the value of EMF across the two ends of this copper wire. Okay, so now if you can see what we are having actually a junction in between constant and iron wire. Okay, and other end of both these two wires is actually also made one junction, and particularly that junction is actually dipped inside a ice water mixture. Okay, so obviously if we are doing this at atmospheric pressure condition, corresponding to that our temperature, reference temperature, will be nothing but close to 0 degrees Celsius. Okay, so we are maintaining some reference junction with a temperature of 0 degrees Celsius. Okay, and now what will be happening corresponding to this circuit, while we will be actually changing the temperature at this particular junction, corresponding to that we will be getting the changes in our output voltage, and as already we are having these junctions maintained at some fixed reference temperature, so now we can relate the value of temperature at this particular junction directly with the value of the EMF whatever we will be obtaining over here. Okay, So it means when we have to employ the thermocouples for our actual measurement in the practical scenarios, particularly in order to obtain the absolute value of the temperature, under these circumstances, what we have to do, we have to create some reference junction over here. Okay. Now, in this particular arrangement, you can see we have nothing but created this first reference junction, and then we have created one more reference junction. So this type of two reference junction arrangement is needed if the temperature at these particular terminal points where we want to do the measurement is actually different. For example, if I consider that at this first particular terminal, we are having our temperature as nothing but T1, and at the second terminal point, if temperature is T2. Okay, so if the temperature of these two terminal points where we are across which we are measuring the value of the final output EMF, if that temperature is different, then actually we need to have nothing but two reference junctions over here. Okay. Now we can consider one more arrangement. So over here you can see we are having one constant wire, and then another wire also we have taken over here as of constant only, and in between we are having one iron wire. So now the iron constant is actually making two junction points. So at first junction point we are having nothing but our unknown temperature. Okay, and at the second junction point we are having the reference temperature. So this type of a single reference point based arrangement is actually applicable when we consider that temperature of this T1 terminal and T2 terminal, these temperatures are nothing but same. Okay, so if our both the measurement terminals are having same value of temperature, corresponding to that, only single reference junction will be actually sufficient enough to provide us or to relate the value of unknown temperature with the output whatever we will be getting from the circuit. Okay, so this particular reference temperature is very important, because if this junction is not maintained at some constant reference temperature, then obviously what will be happening, if this temperature is actually changing, because of that what we will be having, we will be having some axial conduction of the heat, and that axial conduction of the heat will be actually changing the temperature at this particular junction also. Okay, so in that case what will be happening, EMF will be nothing but influenced by the change of temperature at both the junctions. Okay, so in that particular situation, what will be happening? We will not be able to relate directly the value of this unknown temperature, okay, to the final output EMF, because over here the temperature of this second junction will also be changing. Okay, so the whole idea of maintaining or using the reference junction is to maintain constant temperature at this particular point. So if we are having a constant temperature at this particular point, then obviously whatever the changes we will be having in our EMF, that will be only caused because of the temperature, which is unknown temperature, which is subjected at this particular junction of measurement. Okay, so if our temperature points, if our temperature at terminal points is actually same where we are doing the measurement, then obviously a single junction, single reference junction will be actually serving the purpose. Okay, so now what we are having while we do the measurement using thermocouple, obviously output we are getting nothing but our EMF. Okay, and input parameter, we are actually subjecting a temperature field at our sensing junction point. Okay, so here we are subjecting this particular junction to our point of measurement. Okay, so what we should have now, we should have some relationship in between the EMF and the temperature, then only we will be actually able to find out the corresponding value of the temperature. Okay, so generally what is done, this one type of cubic relation is given over here, that EMF is nothing but equal to A times T plus half of B times T square plus 1 by 3 C times T cube. Okay, so this is the general third order polynomial which is taken over here in order to relate the value of output EMF as function of temperature. So over here this T is nothing but unknown temperature. We are considering it. Obviously, while we will be calibrating our thermocouple for the first time. So at the time of calibration, actually, we have to maintain this temperature should be a known value, and corresponding to that, we will be measuring our output voltage, and then we will be developing some relationship in between the output voltage and the known temperature field. Okay, so once our instrument is calibrated, so while we will be using that particular instrument, then what we will be doing actually, by just knowing the value of the EMF, we will be able to relate it to the corresponding temperature. Okay. So this is one detailed table, which actually gives the value of thermal EMF, which is obtained or generated inside a thermocouple, and this EMF is actually given in absolute millivolts. So millivolts is the unit over here, and for different temperature value, we are having the different value of EMF over here. Okay, so now obviously, as I have told you, that in case of measurement of the temperature, what we have to do, we have to consider two different materials. So we will be having one material, and then another wire will be of some another material. So that's why you can see over here, while I have given the table of this thermal EMF, which is generating as a function of temperature, so it is actually given for specific arrangement of the two materials. For example, first over here, it is nothing but in between copper and constantan. So one material is copper, and the material of the second wire is constantan. Then we are having this chromel and constantan, iron and constantan. So these are the different standard materials actually which are used for this commercially available thermocouples. Okay. Now you can see we are having some nomenclature of the thermocouples also. So you can particularly see the corresponding nomenclature which is commonly used, that is also given over here. For example, copper constantan type thermocouple is known as T type thermocouple. Chromel constantan is known as E type thermocouple. Similarly, we are having J, K, S and N type thermocouples. Okay, so if you just try to search the thermocouples for using in your experimental facility, and if you just talk to a vendor, he will be very first question he will be asking you that what type of thermocouple you require, and what is the range of your measurement, because you can see over here, while we have given the values of EMF for T type thermocouple, it is given from -150 to 400. So this is the actually range of its operation. Okay, beyond which this T type thermocouple will not be working. Then similarly, we are having E type, J type, K type thermocouple. So always we have to actually know first the range of our temperature measurement, and then accordingly we can select that what type of thermocouple will be serving our purpose. Okay, so we are having certain alloys also over here. So you can see in this particular table, so the composition of the different alloys is also given. Okay, apart from that, whatever the EMF value is given over here, so what we are having nothing but a one junction, as I have told you, and then another junction we will be actually creating as a reference junction. Okay, so in this particular table, whatever the values are reported over here, these are nothing but corresponding to that of reference temperature of 0 degree Celsius. Okay, so we have considered 0 degree Celsius as reference temperature, while we have actually given the value of different thermal EMF which are obtained. Okay, so the meaning of this particular temperature is nothing but if I subject this junction to -150 degree Celsius, then corresponding to that I will be getting this value of -4.648 if I am using a T type thermocouple arrangement. Okay. So this is like very important table, because if I know that I am having some calibrated P type thermocouple or E type thermocouple, then by just knowing the output voltage, I can refer to this table, and then from there I can relate it to the corresponding value of the temperature. Okay. So these are the error limits which are given for commercially available thermocouple. So for example, we are having different type of thermocouple. So you can see over here E, J, K, N, R, S, T. So these are the thermocouples we are having, and the corresponding error you can see over here if you are using the standard grade thermocouple, and if you are using a special grade thermocouple, then also the corresponding error value is given. Okay, so you will be finding that with the special grade thermocouples, always we will be having less error in comparison to the standard grade thermocouples. Okay, so while you are selecting the thermocouple for your actual experimental apparatus at that particular point of time, you have to also consider the error requirement, or the error of your measurement device also while selecting a type of thermocouple, because you may find that within the range of your temperature measurement, two or three type of thermocouples are actually satisfying the range of its operation. Okay, so these can be employed. But what will be happening if your error of measurement or sensitivity of measurement is actually very precise, then obviously you have to select the type of thermocouple which is having the least error. Okay. Then what I have done over here, nothing but it's once again whatever the table I have presented, that table is actually presented in the graphical format. So this I think I have missed this particular value over here. So this title of this slide is not correct. It is not error limit, rather it is nothing but the thermal EMF. Okay. So it is nothing but thermal EMF for commercial thermocouple. So whatever the thermal EMF earlier I have presented in the form of a table, that is now actually given nothing but in graphical form. So you can see this EMF in millivolts is plotted actually along the ordinate, and along abscissa we are having the value of temperature, and scale of temperature is actually given in Fahrenheit as well as in degree Celsius. Okay, and over here you can see the reference junction is maintained at nothing but 0 degrees Celsius. This I have told you previously also, that our table is actually obtained for reference junction at 0 degrees Celsius. Okay, and these 1, 2, 3 are given as the legends of different lines. So or ABCD is also given as legend. So you can see the corresponding types of the thermocouples to these legends. Okay, so these are also given. So this is nothing but whatever the table I have presented you earlier, that table is given in actually graphical form. Okay. Then I have already given you one relation, that whatever the output EMF we will be getting, that is nothing but A plus 1 by 2 Bt square plus 1 by 3 Ct cube. Okay. So now if we have to determine the sensitivity of our device to the change in temperature, so obviously what we have to do, our output is EMF and input is temperature. So we will be finding that how much change is there in our output to unit change in our input parameter. Okay, so because of that, what we will be doing, our sensitivity is nothing but equal to dE by dt. Okay, so if you do the dE by dt using the previously fitted equation, you will be finding your dE by dt is nothing but A plus bt plus Ct square. Okay, so what I have done over here, I have actually given the thermoelectric sensitivity of thermo element, which is made up of different materials, and particularly all these materials what are listed over here, these are actually used against platinum. So it means, as I have already told you, that we will be having two different wires. So obviously the first material is something which I have listed over here, and second material is actually fixed for all the cases, because we want to show over here the sensitivity value against some fixed material. So that second material of the wire is actually taken as platinum. Okay, so corresponding to that, if you just see the unit of sensitivity is given over here in micro volts per degree Celsius. Okay, so if you use bismuth, constant, and nickel, so depending upon the type of the material, you are having the different values of sensitivity. Okay, so this table is actually very important once again while deciding the type of thermocouple to be employed for your measurement, because if your phenomenon is very sensitive, then obviously you have to consider the high sensitivity material, for which the change in voltage is actually significant for unit change of the temperature. Okay, and if your measurement is actually having the requirement of large range of measurement instead of having very sensitive to the minor changes in temperature, then obviously you can go for the low sensitivity type materials. Okay. And this is one very common table once again. So this particular table actually shows the operating range of thermocouple. So over here along the ordinate we are having once again the value of temperature in degree Celsius as well as in degree Fahrenheit. And over here this range of the range of operation of different thermocouples is actually shown over here. So you can see we are having over here T type, J, E, K, these are the different type of thermocouples whatever we are having. So we have given over here two types of things. So one is generally satisfactory and second is operational but not recommended. So it means wherever we are having this white range, so in this particular range our thermocouple will be actually giving the satisfactory operation. Okay. However, wherever we are having the gray shades on our this histogram, so in this particular range of the temperature actually we can employ this particular device, but obviously the measurement or whatever the measurement we will be getting, that will not be very accurate. So that's why its use is actually not recommended. Okay. Then these are some of the thermophysical properties of common thermocouple materials. So you can see over here we are having different materials over here and their corresponding thermophysical properties like thermal conductivity, specific heat, density, electrical resistivity, temperature coefficient of expansion and melting point. Okay, so all these are the properties which are very important, because later on in this module only, particularly which is on measurement of temperature, we will be studying one section on effect of heat transfer on measurement of temperature. Okay, so what basically happens if our heat transfer is actually happening across the length of the thermocouple, then that will be actually altering or that will be leading to certain inaccuracies in our measurement of temperature. Okay, so while we will be studying that particular section, at that time the requirement of these properties will be there. Okay. So this is one more table. Actually, in this particular table, what we are trying to do, we are trying to relate the value of temperature with voltage with the help of some polynomial fit. Okay, so this is a higher order polynomial fit which we are considering over here. Okay, so like what is the need of using this type of polynomial fit? So let me first explain this to you. So what will be happening while we will be using our thermocouple device? So obviously we will be having this kind of arrangement. So where we are having first material, second material, then we are having some reference junction, and then we are actually obtaining the value of the EMF. Okay, so it means we will be having some wires of two different materials, and the junction of these wires will be actually at our sensing point, okay, where we want to measure the temperature. Now corresponding to that we will be getting some output voltage. So obviously in this particular at this particular location we require certain electronic circuit or certain arrangement or certain device which will be measuring the value of this EMF. Okay, so generally what we are having some voltmeters which will be giving us the value, corresponding value of the voltage. Okay, so obviously if we have to simply if we are simply measuring the voltage, that is something which can be done, that we are measuring that voltage and then corresponding to that type of the thermocouple we are actually going to its calibration curve, and from the calibration curve we are obtaining the value of the temperature. Okay, so that is something which will not be always possible, because in majority of the in many of the application there will be requirement that we want to instantly know the value of the temperature. Okay, rather than first obtaining the data of the voltage and then obtaining the corresponding value from the calibration curve, we have to actually immediately or instantly know the value of the temperature. Okay, so that's why what we do, we particularly use some additional system over here. Okay, so we use some additional system, and in this additional system what we will be doing, we will be having some voltage measurement circuit, which will be giving us the value of the voltage, and then we will be having some small microprocessor over here. Okay, so we will be having some microprocessor. So this voltage data will be going inside the microprocessor, and out of the microprocessor we will be nothing but getting the corresponding value of the temperature. Okay, so it means we require certain additional device, certain microprocessor, which will be actually processing our voltage signal, and that will be then converting that voltage signal into nothing but the corresponding temperature field. Okay, so how this is accomplished? So what we have to do inside this inside this microprocessor, we have to do certain operation, and that certain operation is actually converting our voltage value into the temperature value. Okay, so for that reason, what we do, we actually take some polynomial relationship in between the temperature and the corresponding value of the voltage. Okay, so this x over here is nothing but representing the value of the voltage whatever we are getting for some temperature, and a2 a1 are nothing but the coefficients, and over here this generalized polynomial I have shown over here is nothing but ninth order polynomial. Okay, so now for this polynomial, when we will be calibrating it for the against the known temperature, then obviously we will be able to find out the corresponding value of this coefficient, and we will be knowing the relationship in between the voltage and the temperature. Okay. So for different type of thermocouple, for example, if we are having type E thermocouple, type J or K, depending upon the type of the thermocouple and its range of operation. For example, for first range, we are having -100 to 1000 degrees Celsius, then accuracy of plus minus 0.5 degrees Celsius. So over here, if we consider the ninth order polynomial, then these are the nothing but corresponding value of the coefficients. Okay. Then for this second type of thermocouple J, we have actually considered the fifth order polynomial within its range of application from 0 to 760 degrees Celsius. Okay, so likewise, we are having the range of operation mentioned and the order of this polynomial, and the corresponding value of the coefficients are given over here. Okay, so this particular relationship is actually very useful for designing the additional system which is connected to the thermocouple in order to obtain the final process value of the temperature from our thermocouple device. Okay, so that's why like you will be knowing, if you have used the thermocouples earlier, that depending upon the type of the thermocouple, many times we are having actually thermocouple type specific post processing units. Okay, or apart from that also we are having some generic data acquisition systems or generic temperature processing units, which will be actually inside which actually we have to select the type of the thermocouple whatever we are using. Okay, so we have to specify the input that okay, this is our type of thermocouple which we have physically connected to the channel. Okay, so depending upon that, actually it will be using the relationship, this polynomial relationship, and finally the microprocessor whatever is installed inside that system, that will be doing the calculations, and finally that will be giving us the corresponding value of the temperature. Okay, so this is one important thing which is actually mainly used. So many of the times we do gross blunders also. So for example, if we are considering certain post processing unit, we may do that we have taken a post processing unit for K type thermocouple, but we are trying to connect E type or J type thermocouple to that, and then we are saying that okay, our value of the temperature is not coming correct. Okay, so this type of things actually we have to take care while we are employing thermocouples into our experimental measurements for measurement of the temperature. Now, one more important point I would like to highlight at this particular point, that always it is not possible to have reference junction while we will be doing the measurement. Okay, because as I have told you that while we are doing the measurement of temperature using the thermocouple, if we are doing the absolute measurement, then we require certain reference point or reference junction with reference to which actually we will be getting our absolute value of the temperature, okay, depending upon the output EMF. So that is something which is not feasibly practically feasible, because by meaning this means every time if we are using a thermocouple, we have to actually spend some additional cost on creating some reference point and then calibrating our system, and always we have to actually maintain the temperature of reference point to some fixed value, okay. So as it is not practically feasible, so because of that, whatever the post processing unit I have told you we use for the thermocouples, we are having some reference junction compensation, particularly using the thermistors inside our system itself, okay. So here you can see this is our thermocouple bead, which will be our sensing point, and then we are connecting this to our circuit. So in our circuit actually you can see this is our additional circuit which we are using as a compensation circuit, okay. So inside this we are having a thermistor. I have already told you that thermistor is having actually in our previous lecture, that in case of thermistor, if temperature is increasing, its resistance actually decreases, okay. So over here we use this thermistor, and this acts as nothing but compensation instead of the reference junction, okay. So the resistance of this thermistor is nothing but RT. Then we are having some variable resistance over here, Rx, okay. And then we have this VB as some supply voltage, and this RA we are having two additional resistances over here. And what we are doing, we are trying to actually measure the final delta V readout over here, okay. So what generally we do, the very first thing we do is actually we maintain this thermocouple bead corresponding to 0 degrees Celsius. Okay, so initially we will be maintaining it at 0 degrees Celsius, and while we are maintaining it at 0 degrees Celsius, at that particular point, what we will be doing, we will be actually varying the value of this variable resistance Rx, and we will be adjusting it in such a fashion so that corresponding to 0 degrees Celsius, we are getting nothing but delta V value as 0 millivolts. Okay. And then once we have adjusted this, after that, what we are doing, we are actually supplying over here this VB as some voltage. Okay. And then we are using this thermistor, which is having some resistance RT. Okay. So what generally we do, that we try to select the value of this particular input voltage VB and this RT in such a fashion so that we are having a linear relationship in between temperature and the corresponding value of delta V which we are getting outside over here. Okay, so we are actually trying to obtain this circuit, particularly trying to choose the value of this VB and RT, and we also use this additional variable resistance over here. The sole purpose of using the additional variable resistance is that by adjusting the value of this variable resistance corresponding to 0 degrees Celsius temperature, we are actually maintaining the corresponding delta V readout as nothing but 0 millivolts. Okay, so this is one additional circuit. If we use this additional circuit, in that case, we need not to connect uh, or maintain a reference junction over here. Rather, our thermistor will be actually doing the task of the reference junction. Okay. Then another important arrangement, we are having this particular type of arrangement is known as thermopile connection. So we may have certain type of thermocouples or certain physical situation where we are having actually difference between the temperature at two different junctions as very small. Okay, so if we are having very small temperature difference, then obviously whatever the output voltage we will be getting, that will be actually very small magnitude. Okay, so in that case, what will be happening? We will be having nothing but low sensitivity of our device. Okay, so if you have to maintain or increase the sensitivity of the device, in that case, what we can do, for example, these are my 2 points. Say T1 I can consider as the point at which I want to actually measure the temperature, and T2 I can consider as my reference temperature. Okay, Now, if I consider a situation that this T1, T2 block, my reference block is having nothing but entire periphery is having uniform temperature. Similarly, the entire spatial location of this unknown temperature is also actually having the uniform value. So means everywhere it is having T1 value and it is also having everywhere T2 value. Okay. So in that situation, what I can do, I can actually create the multiple junctions. For example, this is one junction I have created over here, then another junction I have created over here, and then one more junction I have created over here. Okay, so you can see over here we are having nothing but the material dissimilarity over here, and over here also we are having dissimilar material. Here also we are having the dissimilar material. Okay, so in this particular type of arrangement, now you can see that nothing but we are measuring this temperature, and this we are considering as our reference temperature. But when we were having the only single junction corresponding to that, we were getting, say, if some output as say E dash. Now when we have used the three different junctions between the same temperatures, considering that the temperature of each junction is same, corresponding to that, whatever the output we will be getting, that will be nothing but three times that of the original output by using the single junction. Okay, so it means this type of arrangement, thermopile connection based arrangement, can be employed if we want to go for the amplification of the signal. Okay, or we want to increase the sensitivity of our measurement field. Then this is the series connection between the thermocouple. So you can see we are having these four different junction points A, B, C, D, and then we are connecting dissimilar materials between these junction points. Okay, so this type of connection is something which is known as series connection, because in series we are connecting the different thermocouples, and then at this particular junction actually we are obtaining the value of output voltage. Okay, now you can see the terminal points at which actually we are measuring the value of this particular output. Corresponding to that, if I consider this thick line as nothing but my material 1, okay, and this thin line as material 2, and this thick line once again as material 1. Okay, so in this particular arrangement you can see that at each and every measurement point we are having nothing but the same material which is connected to the output. So that's why over here we need not to go for the reference junction. Okay, so now in this arrangement, if we consider that current will be flowing from this positive to negative side, so obviously we will be having flow of current like this. So because of that, what will be happening, whatever the potential we will be getting on these terminal points, so between the consecutive terminal points, we will be having opposite potential, then only our current will be actually flowing in this particular direction. So because of that, at this, whatever the direction of potential we will be having at this junction A, the direction of potential at B will be reversed. Similarly, C will be having same, and then D will be having reverse. So it means A and C will be having the same direction of potentials, and B and D will be having different directions of potential. So because of that, whatever the final output we will be getting, that will be nothing but EA minus EB plus EC. Okay, or I am just doing a mistake. So over here, what will be happening? This is having positive. So obviously, at this point, if current has to flow, this will be going in negative direction. Then this has to be at positive. This has to be at negative, and this has to be at positive. Yeah, so I have written correctly. So what will be happening? E will be actually whatever the final output we will be measuring. That will be nothing but EA minus EB plus EC. Sorry. So I have considered negative as minus. Yeah. So EA minus EB plus EC minus EB. Okay. So that will be my final EMF, whatever I will be obtaining from this series circuit. Okay. Now, from this series circuit, we will be having actually final EMF will be coming from this type of arrangement. But the only issue is that because we are having now four different junctions. Okay, so obviously these four different junctions will be having actually some value of the temperature. Okay, so it will be like what we have to do if we are employing this type of circuit for measurement of the temperature. Then obviously we can vary the temperature only at a single junction, and other three junctions actually we have to maintain at certain constant value of the temperature. Okay, so this type of arrangement is actually very complicated, and it is not mainly used for measurement of temperature. Okay, then we are having parallel connection of thermocouple. So for example, you can see over here, this we are having four different junctions, T1, T2, T3 and T4, and parallelly then we have connected the thermocouples to each of this junction, and then we are measuring the value of the final output voltage. Okay, so if in this particular type of arrangement, what will be happening, whatever our output EMF we will be obtaining, that output EMF will be nothing but proportional to the average temperature of these four different junctions. Okay, so from this type of parallel thermocouple connections, actually we can obtain the average temperature of the different junctions. Okay, and particularly if you have to obtain the average temperature, then apart from using the parallel connection, we can also go for the thermopile like connection arrangement for measuring the average temperature. For example, in case of thermopile, what we can do, if this is my say reference temperature of T2, so obviously the reference temperature I have to maintain at some constant point. So everywhere I should have the constant temperature. Okay, and if I consider that this is some unknown temperature which I want to measure, then corresponding to the this particular location, say I have different values of temperature, T1 dash, T2 dash and T3 dash, then obviously whatever the final output I will be getting, if I divide that final output divided by the number of junction points I am having, a number of junction points of unknown temperatures I am having. So in that case, what will be happening? This E by N signal will be nothing but proportional to average of these three different values, T1 dash plus T2 dash plus T3 dash divided by 3. Okay, so parallel arrangement is having the advantage that if we are having some multiple unknown temperature, if you want to measure their average only, so then output is actually directly related to the average temperature. Okay, another means of obtaining the average temperature is actually by using the thermopile like connection, that in case of thermopile, the reference junction will be maintained at same uniform temperature at each and every junction point. However, the unknown junction actually will be having different temperatures. So obviously, whatever the output we will be getting, if we divide that output by the number of junction points, so that will be nothing but proportional to our average temperature of these unknown junctions. Okay, so now this is very important about the installation of the thermocouples, because while we are installing the thermocouples, if thermocouple is not properly installed, so we will be getting significant errors in our measurement of temperature. Okay, so the very first way of locating the or installing the thermocouple is shown over here, where actually whatever the junction we are having in between two different wires, that junction is actually, that junction point is only contacting the surface where we want to measure the temperature. So this is the accurate method of connecting the thermocouple. So in this case, what we will be getting, we will be only getting the value of temperature at this particular junction point. Okay. Then another arrangement what we have done, now we are having this as our surface where we want to measure the temperature, but the two whatever the two wire ends were there, these we have not actually made as a junction, rather we have connected these to our surface at different points. Okay, now if our this surface is actually a metal, in that case what will be happening, this will be also participating as nothing but a third material. Okay, so because of that we will be able to obtain the corresponding we will be able to obtain the value of EMF, and that EMF then we can convert it into the corresponding value of the temperature. Okay, but in this particular arrangement, what will be happening, at this first junction point we may have some different temperature, and at this point we may have some different temperature. Okay, so whatever the output temperature we will be getting, that will be nothing but the average of the temperature which variation which is actually happening in between this shortest path between these two terminal points. Okay, so if we are having the different temperature on the parts of the surface, then obviously whatever the final temperature we will be getting, that will be representing some average measure of the temperature between these 2 points. Okay, then the third situation is, though we have over here connected our thermocouple correctly to the surface, but after that what we have done, we are having some this contact, physical contact in between the wires, metallic wires. Okay, so in this type of arrangement, what will be happening, while you will be obtaining the output EMF, that will be actually giving you the value corresponding to that of the temperature at this particular sort point rather than the temperature at this particular junction. Okay, so in this case also, whatever the temperature you will be getting, that will be nothing but your faulty temperature. Okay, so one has to take care of this thing that while we actually, what we do generally while we use the thermocouples in our measurements at laboratory for the laboratory purpose. So what we do, we actually purchase some rolls of commercially available wires, and then what we do, we actually by ourselves, we actually try to create some bead of the thermocouple. Okay, so while we are creating the bead of the thermocouple, whatever the insulated portion we are having over that metallic wire, we remove some insulated portion. Okay, so we have to take care of this thing, that our thermocouple should meet only at the bead point, and apart from that, there should not be any metallic contact between the two wires. Okay, otherwise, what we will be having, we will be having errors in our measurement. Okay, and moreover, one more important thing we have to consider, that when we purchase the commercial rolls of the wires in order to prepare our thermocouples, so obviously what will be happening, each depending upon the grade of the wire, we will be having different error limits and uncertainties associated with the measurement of temperature. Okay, so if we are using the two different thermocouples from same roll of the wire, and our sole purpose is only to measure the temperature difference between these two values. Okay, and the two thermocouples which are employed, these are taken from the same roll of the wire, then obviously we need not to much worry about the errors associated, because we are mainly interested in the difference of phenomenon between 2 points. Obviously, whatever the error is associated at the first point, almost same amount of error will be associated to the second point. Okay, so in that case, actually we will be having less inequalities in our measurement. However, if we are using some thermocouple for the measurement of absolute value of the temperature, in that case, obviously what we have to do, we have to ensure, or we have to properly calibrate our device. Obviously calibration is needed in both the arrangements, but while we are calibrating actually, or while we are considering the sensitivity and error associated with the thermocouple, then we have to be very precise and accurate in measuring the amount of error. Okay, otherwise we will be having we may have significant issues with our final value of the temperature. Okay, so some of the common errors which happens while using the thermocouples for practical applications are mentioned over here. So we may have junctions which are formed by users, and these may involve excessive temperatures or faulty soldering techniques. Okay, so for example, while you are fabricating the thermocouple bead, so at that time, while we are creating this junction, so we may have this excessive heating because of the soldering. So such type of issues will be actually causing errors in our measurement. Okay, then another type of issue could be that thermocouple may be used outside their applicable range. So that is one very important point which we have to consider, that if we are employing the thermocouple outside its range, so obviously one thing can be that it may give us the results which are not accurate, and apart from that, what will be happening if we are using it over a period of time, so then also actually the calibration of the thermocouple is changing. Okay, then we may have faulty reference junction compensation. Okay, so sometimes while you are using the reference junction, so these may be faulty, so we have to take care of these things also. Then installation faults may occur. For example, I have shown over here these two types of installation faults. So if we are not properly installing the thermocouple, then also we will be having significant errors. Okay. Then the user may install wrong type of thermocouple for readout equipment. So as I have told you that each thermocouple is nothing but uh, requires some readout circuit also. So if we are using the wrong type of the thermocouple and we are connecting it to some another readout equipment which is not designed for that type of thermocouple, in that case also we will be getting inaccuracies in our measurement and errors, and particularly this type of errors are nothing but referred to as gross blunders. Okay. Then one of the important technique for measurement of the temperature is actually known as quartz crystal thermometer. So quartz crystal is actually having a very unique characteristic that the resonant frequency of this type of crystal is actually sensitive to the temperature change. Okay, so if we are just measuring the resonant frequency of the quartz crystal for the different values of the temperature, then obviously it is having direct relationship. So based on the changes in resonant frequency, we can determine the corresponding value of the temperature. Okay, so what we are having when we are having the proper angle of cut with the crystal. So in that case, what will be happening while the crystals are actually cut? So at proper angle of cut, if we are having corresponding to that, we will be having linear relationship in between the resonant frequency and the temperature. Okay, so for example, if we plot the frequency as function of temperature, so we will be having some linear relationship. Okay, so obviously if our relationship is linear, so directly by knowing the value of frequency of oscillation of the quartz crystal, we can determine the corresponding value of the temperature. Now in this particular arrangement, so generally what we are having some small cell type structure where we will be actually physically locating our quartz crystal, and this quartz crystal will be actually oscillating over here. Okay, then obviously at the boundaries of this cell we will be having certain thermal contact to the area where we want to measure the temperature. So corresponding to that, the oscillation pattern or the resonant frequency of oscillation of this quartz crystal will be actually changing. Okay, so we require certain electronic counter which will be measuring the value of the resonant frequency of these oscillations. Okay, and then we will be having certain digital readout which will be reflecting the value of the frequency measurement. Okay, so for absolute measurement of the temperature, usual sensitivity of this type of device is actually very precise. So it is of the order of 0.001 degree Celsius. Okay, and this device has normal operating range of -40 to 230 degrees Celsius and frequency temperature relationship of about 100 Hertz per degree Celsius. So corresponding to 1 degree Celsius, you may find the change in frequency of 100 Hertz. Okay, so this is very accurate method for measurement of the temperature. Okay. Then another important technique is also there, which is referred to as liquid crystal thermography. So in case of liquid crystal thermography, we are having actually some liquid crystals which are formed from esters of cholesterol, and these particular liquid crystals actually these exhibit some interesting response to the temperature field. Okay, so what is that interesting response? That when we will be subjecting it to the temperature change, then these liquid crystals will be actually exhibiting color of visible spectrum. Okay, so it means if we will be subjecting these liquid crystals to some temperature change, then depending upon the value of the temperature, these will be actually giving us the spectrum of visible light. Okay, so these operates from close to 0 degrees Celsius to several hundred degrees Celsius. Then temperature range or temperature at which the color changes can vary from 1 to 50 degrees Celsius. Okay, so the whole idea is that that, for example, if this is my surface and I want to measure the temperature of this surface, and this particular surface, say, if it is having some source of heat generation at its center, and then whatever the heat is actually generating, that is spreading across the entire periphery of the surface. So what I will be doing, we will be first do the spray coating of this surface. Okay, so we will go for spray coating. So by using spray coating, actually we will provide a layer of liquid crystals over this entire surface. Okay, so now what will be happening, this particular source of heat generation will be actually causing some high temperature at this particular center point, and correspondingly, as we will be moving away from the center location, we will be having actually decrease of temperature. Okay, so we will be having some thermal gradient in the outward radial direction. Okay, so because of that, what will be happening, because now we have provided some spray coating of the liquid crystal. Now we are having thin layer of liquid crystals over here. So these are now adhered to the surface. So obviously these liquid crystals will be actually showing some changes in the color. For example, the crystals which are at highest temperature, these will be having red color, and as we will be moving towards the lowest temperature side, we will be having actually blue color, and in between we will be having the change of spectrum of colors within the visible range. Okay, so what we can do now, we can take the photograph of this particular surface, for which where we are having actually the different spectrum of light, and then we can obtain the corresponding we can employ image processing for obtaining the corresponding RGB values at each and every pixel locations, and then we can relate these RGB values to the corresponding value of the temperature. Okay, so for example, this one important line is written over here, that temperature range for this type of liquid crystals uh, at which color will be changing can vary from 1 degree to 50 degrees Celsius. So depending upon the type of crystal we are using, for example, if I want to use for small measurement, it may happen that I'll be getting red color corresponding to 50 degrees Celsius, and then at 40 degrees Celsius I'll be having yellow color, and similarly I'll be having other spectrum, and say my minimum value blue color is corresponding to 10 degrees Celsius. Okay, if I want to use it for the precise temperature measurement, then obviously what I'll be having another color scale where red will be corresponding to 10 degrees Celsius and blue will may be corresponding to 5 degrees Celsius. Okay, so what we will be doing, nothing but we will be taking the photograph of the surface where we want to measure the temperature, and then that particular photograph actually we will be relating to our color scale, whatever we are having, that corresponding to what type of color we are having, what value of the temperature. Okay, that we will be actually relating using nothing but our image analysis. Okay, and as in image analysis, if we are having high resolution of the camera with which actually we have taken this particular photograph, so we will be having actually very close spatial contour of the temperature profile. Okay, now in order to prevent the liquid crystals from deterioration, these can be coated with polyvinyl alcohol, and these nothing but produce some encapsulated liquid crystal. So there will be some protective coating layer uh, on the periphery of the liquid crystals. Okay, so the resolution of measurement of temperature is around 0.1 degrees Celsius. Then digital imaging, where pixel by pixel readings may be taken of color and illumination intensity across the image are applicable to the technique. So what we will be doing is nothing but taking the photograph, and then we will be processing it using the image analysis. Okay, for obtaining the corresponding value of the temperature. Then we are having another technique for measurement of the temperature by radiation. So what I will do now, I'll stop at this point, and we will study about this particular technique in our next lecture.